Okay, in the last part of this lecture, we derived the perturbed result for the orbit of planets. And the important part is this compare with unperturbed, there's this actual 1 minus epsilon term. The epsilon is related to the uh, Schwarzschild radius, the small quantities, so small correction. Uh, because this term, the planet returned to its perihelion, mean not at the phi equal to 2 pi, but at the 2 pi over 1 minus epsilon, because then cancel 1 epsilon, then it's cosine 2 pi again. So 2 pi over 1 minus epsilon can be written as 2 pi times, it means put this in the numerator, uh, as 3 pi r star over alpha. So uh, the perihelion advances. It was the whole orbit rotate in the same direction as the planet itself per revolution by this amount. But this extra factor is 3 pi uh, Schwarzschild radius over alpha. Alpha turned out to be, we have seen previous slides, is 1 plus uh, electricity times the R mean. Okay. So therefore, uh, if you put in the fact that the R star is radius, Schwarzschild radius for the sun, which is 2.95 kilometers, and Mercury eccentricity E is 0.206, and its perihelion R mean is 4.6 10 to the 7th kilometer. Okay, you plug these numbers in, you find this the advance of precession is 5.0 10 to the minus 7th radian, of course, per revolution each time they go back. Uh, Now, if you convert this result in terms of arc second per century, we'll do this. Uh, First of all, to change radian in terms arc second, you first of all, pi radian is equal to 180 degrees. So I multiply 180 degree divided by pi, and then 1 degree is equal to 60 minutes arc second, and 1 arc second minute is equal to 60 arc second. So we'll put all these factors in. We notice, of course, the degree cancel, minute cancel, radian cancel. So left was only the arc second, and you will multiply this factor out. Point 1/10 of arc second per revolution, just tiny little bit advanced. Okay. Now, if you in terms advanced per century, this 0.103 arc second, you per revolution, and each revolution, each period for Mercury is 0.241 year. And then you, in terms of century, you by 100 year divided by century. So the year cancel, you get arc per century, which is turned to be 43 arcsec per century, precisely as was observed. Okay. Uh, the calculation explained the perihelion advance of the Mercury from first principle, and the correct prediction of the bending of starlight by the sun were all obtained by Einstein in an intense 2 week period in November of 1915. Afterwards, she wrote to Arnold Sommerfeld in the now famous letter. Okay. Uh, the last month I have lived through the most exciting and the most exacting period of my life. It will be true to say it has been the most fruitful. Writing letter has been out of question. I realized up until now that my field equation of gravitation had been entirely devoid of foundation. When all my confidence in the old theory vanished, I saw clearly that a satisfactory solution could only be reached by linking it with the Riemann variations. The wonderful thing that happened was that not only did Newton theory result from it as the first approximation, but also the perihelion motion of Mercury as the second approximation. For the deviation of light by the sun, I obtained twice the former result. Okay. By the way, writing letters in up until, I guess, until the 1950s, physicists, when they finish a piece of work, they usually write letters to their friends telling them the results. The idea of preprint haven't been invented, haven't been occurred to people to do that. And in fact, I knew someone who said, "I know, I just never thought about it. It was such a wonderful thing to have the preprints." But anyway, this is the famous letter. And of course, Einstein was extremely excited. And in fact, his biographer, Pice, said this is by far the strongest emotional experience in Einstein's scientific life, perhaps in all his life. By the way, also, we already talked about recovering the Newton's solution, the Newton's field equation, and Taka-Link's Riemann variation. This actually is just what we now call Einstein's uh, curvature tensor. For the remaining part of this lecture, basically I will talk about the homework exercise 6.3. Uh, we about light deflection by way of geodesic equations. Previously, we obtained the light deflection by using the effective index refraction and the Huygens principle. Now we can obtain this by way of GR equation motion, just as we did for the uh, planetary orbit. I'd like you to obtain the uh, light deflection result by follow exactly the step as we did for the Mercury orbit. Okay, but now the energy balance equation is not L equal to minus c squared for test particles mass. For lights, it turns out you should remember the full velocity square is, or rather the L is equal to 0. Okay, so this is a energy balance equation. And then again, follow exactly the same step. You identify the constant motion and express the L equals 0 in terms of constants. Then change the differential from differential the curve parameter to differential back to the orbit angle. Then instead use u one over r as a variable to find the orbit equation. Now this is different from the Mercury because we're talking about L equals 0 equation, and the epsilon here is for 3r star, the Schwarzschild radius over 2. And solve perturbatively, just exactly the same we did, just the zeroth order, and you find the light is not deflected, and then the small correction. Turns out this could be much simpler than the Mercury case. Then deduce the deflection angle by comparing the direction of asymptotes. Okay, so this is how you can recover the deflection, which is twice as much as equivalent principle. You notice in the newspaper now they all talk about Newton rather than equivalent principle because, of course, first of all, if you talk equivalent principle, no one knows what you meant. So the takeaways from the lecture 15 is the gravitational light deflection from GR is predicted is twice as much as equivalent principle because besides the gravitational time dilation, there's also gravitational length contraction. Gravitational lensing is now an important part of astrophysics tool to find the mass distribution in the cosmos. To find the orbit in space-time, the procedure is basically the same as the Newtonian central force problem. Simple to work with energy balance equation rather than work with the geodesic, F equal to ma equations. In this case, the geodesic equation. And you can find the constant motion by using the Euler-Lagrange equation, and then calculate from first principle. We calculate from first principle the advance Mercury's perihelion, the 40 arcsecond per century advance. Now, the next lecture, actually, we finished GR without the series discussion of tensor in GR. So we can three directions we can go. In the book, I just followed the chapter 7, black holes, and followed by cosmology. Then I came back chapter 11 as sort of appendix chapter on GR tensors. But it really actually for black holes and cosmology, it doesn't involve, it was there are really three independent modulars, so we can go any direction. So I've now decided for the lecture, I will go to chapter 11 first. Okay, remember this is sort of more advanced material. Undergraduate enrolled in physics 4370 are not responsible, but those guys sign up for 55370 should know something about, at least from the review questions. So I could talk because logically it make more sense to talk about this right away since we're fresh uh, study the GR chapter 5, chapter 6, and then we uh, go back to some sense black holes and cosmology. Okay, so and for those who are enrolled in the 4370, you can view some sort of like this semester break. I hope you still look, look at follow the lecture. Basically, I think you want to see. It really is not that hard. It's really not hard, and at least you know what we talk about when people talk about Riemann tensors, so on and so forth.